clicker to work. All right.
Okay, so the last speaker in this session is Rob Schoelkopf. He will be talking about modular quantum computing.
All right, hi. Welcome, everyone. Thanks for sticking around to the end of the day. I want to thank Jake and Ken for inviting me. It's been a really interesting meeting, and so I'm happy to give you a little bit of a update on things going on in the team here at Yale. So yeah, as the title alludes to, I'm going to tell you about a few different ingredients here. So first of all, the modular architecture, and in principle, the ways to make that fault tolerant going forward. We heard a little bit about this already. Then I'm going to speak about what we call hardware-efficient quantum error correction. That's, again, also been mentioned a little bit in this meeting before. Basically, how you can perform the functions you need for making a robust quantum computer using less parts, if you're clever about it, and base things on the physics of the devices. Give you a few of the highlights of us working with these logically encoded qubits in our hardware-efficient approach in a bosonic oscillator. And then at the very end here, I'll tell you about some soon-to-be-published material, which is performing what's called a teleported gate. This is basically the fundamental operation you need in the modular architecture, but a teleported gate where we can actually do in the lab a C0 between two logically encoded qubits. Okay. So you know, just at a very high level to start with, right? You know, I'm very excited about where this field is going. I'm very optimistic about the future. I would say, you know, we had a lot of work to do over the last couple of decades developing the ability to manipulate single qubits, entangling qubits, doing high-fidelity QND measurements and so on that now allow us to address really interesting questions about quantum error correction, about how you build logical qubits and do operations in a robust way. And you know, what I think is really neat here is that maybe now these communities start to come together, experimentalists like me speaking at a QEC conference. You know, so what I would say today is that we know we have the science in hand that it will be possible to build useful systems with these at some point in the future. That's not the same thing as saying it's just engineering from here. Okay, engineers would get very offended at that, right? And that's a sort of a silly thing to say. But you know, we do need and can start now doing the kinds of professional systems engineering that's needed to scale up these systems. But also there's a lot of room for really good ideas and some basic science that tell you better, faster ways to build that quantum computer and get to the goal over down there by the wall, right? Okay. And so again, it means that we can start from the science side thinking about the questions of what's the architecture you use, what's the quantum error correction code you use, and all these sorts of things. So just a brief refresher on this modular architecture. So it has several advantages. Basically, it's kind of a hierarchical way to build a complex thing, which makes good sense. There's some practical advantages for doing this with superconductors in terms of getting very good isolation between your elements and things like that. You can be robust against some failed parts. Essentially, what you do here is you take these modules, which are each going to be essentially small quantum computers that contain your first level logical qubits and do error correction all the time. And then, again, you can do this all in the microwave domain in a superconducting cryostat. You can route signals between these modules to perform measurements or do other kinds of interactions that allow you to build up entanglement between these modules. And then the way you string these together into a set of logical qubits that are a universal and reconfigurable quantum computer is to perform these so-called teleported gates. So now the minimum instance of a module is basically something containing two qubits, the communication qubit and a memory qubit. In the end, of course, this memory qubit is going to be a logical that's error corrected. And you want to do a CNOT between the memory qubits in the two blocks. And the construction for this was put together by Dan Gottesman and Mike Chuang in around 2000. And it sort of looks like this. It may not look, for those of you who aren't familiar with this, exactly like a CNOT. So let me break it down for you. It has several different tasks you have to perform. The first thing you have to do is build an entanglement between your two communication qubits, make a bell pair of some known form, okay? And that, in the end, should be done remotely between these separable modules. Then what you do is some local gates, both two-qubit gates between your communication and your memory qubit. and some single qubit operations on your memory or logical qubit. You have to do measurements in a bell basis on these two communication qubits, and then there's some classical communication and feed forward, okay? And so it looks a little complicated, but it has some, again, nice advantages, right? Which basically means you only really need to get very good at doing these gates within your modules. And this system is separable. You can draw a dashed line here, and the only thing that communicates, except for the classical controls, between them is this sort of bell pair that you need to establish, okay? And so if you look at sort of what's the error probability for a gate of this type, sure, it contains the errors in your local gates. It also contains the errors in this entanglement that you establish between them, and also the error probability that one of these measurements fails. So, okay, that's a hit on your budget. But what I just want to remind you about is that there's a way to basically build these things up and make all of the parts of this robust. For example, the remote entanglement, you can just purify. You're just making a state here, not a gate. So it's only some resource overhead of a few to make at least the first level purification of that. Okay? And so this was described in a paper by my colleague at Yale, Liang Zhang and Misha Lukin and others. Basically, this is what I just said before. You need high fidelity operations within the modules, but you can actually tolerate quite high errors on the parts outside the modules. And so this is kind of appealing to me as an experimentalist. It says, you know, get good at doing a few things, replicate your modules very well. This seems much nicer than making ginormous machines all with 4 nines errors within them. So I think John talked about the Google strategy. I'm going to talk about the Yale strategy. It's sort of the reverse. I don't know how that worked out exactly. We're not sort of focused on what it has to look like in the end and working backwards. We're basically trying to just move forward. And so we're not scaling up the hardware in order to eventually error correct, but basically we're learning how to do error correction well and efficiently now, and then trying to build up a larger machine in a robust way. Okay? And I'm going to talk about the logical qubits that we're working with for me. So I'll make some definitions, and we can have discussion after if I'm misusing terms. But for me, a logical qubit is not something with 10 to the minus 18 order errors yet. Basically, a logical qubit is any way that I can encode a superposition, a bit of quantum information, in a way which is redundant, and when there's some symmetry that I can check so as to monitor for errors and correct them. And I want to point out also that fault tolerance isn't something you just get by adopting a particular mathematical approach. It's something you have to build into the hardware and verify and maintain as you move forward and scale up. Okay? But these are all things that we can actually do in the lab and start testing them and being quantitative about today, which is what, again, I find really exciting on the science side. Okay, so why is error correction hard? Well, first of all, no matter what you do, it's got a lot of complexity. There's many parts you need to put together, and of course, you know, if you aren't careful, you might do a lot of engineering before you really know what works well. There's also something I like to call overhead, right? So this is the obvious thing. As soon as I encode my information now in, let's say, 3 qubits instead of 1, they all 3 can have errors, and so the performance is going to get worse before it gets better. Remember our step back before we take off down the road. Okay. You have to keep the performance high. And another thing I think that's very important is in the beginning, you have to make sure you can debug the thing. And of course, as our system gets more and more complex, all of these are worse. All of these are harder and harder to maintain. And so what we mean when we talk about hardware efficiency is basically trying to realize a logical qubit, building some robust hardware that achieves a useful function with the smallest number of actual parts inside. That helps with all of these aspects. Okay, so if we just look at like what's required to do a error-corrected memory, if you have the standard kind of schemes, and you know, basically it's a lot of hardware you have to build, okay? And with this system we've been pursuing, this so-called cat code that I'll explain in a little bit more detail, we can dramatically simplify at least to get something which is a first-order error-corrected memory for the dominantly occurring natural errors. Okay, so one final comment here in general about logical qubits. You know, on these sorts of charts, it all looks very nice and grand, but this is a very coarse-grained thing. So let's just think a little bit about what it looks like in here. we've been finding this issue a little bit with referee reports. We say, here's the logical qubit, and they say, wait, there's still errors? Yes, in the first instance. So what are some necessary steps that will show you're making progress in the lab towards building logical qubits? So the first thing you have to do is you've decided on some code. You have to be able to build that code. You have to make those code words. You need to be able to measure the error syndromes that you care about. You actually need to be able to measure those in a QND way and very rapidly to track the naturally occurring errors. And basically, the sign that you're making progress here is what we'll talk about in a little bit, sort of demonstrating break-even or lifetime extension. You also need to do operations on the encoded qubit. You'd want to do 1-qubit operations. You want to do 2-qubit operations where you entangle 2 logicals. And then eventually, you want to do all these gates while doing the error correction and have it improve the performance and do a deeper circuit or a computation you can't do otherwise. Okay. So in all the experiments I'm going to show you, we're sort of following this new, for a few years, paradigm at Yale. It's a little bit flipped from the usual way people are using superconducting circuits these days. Essentially, for us, the most important object is this microwave cavity. Here's a block showing sort of 4 of these post-microwave resonators. They can have reliably lifetimes of several milliseconds for a single photon. And of course, because it's an oscillator, it has many energy levels we can access and we can use. So that's going to be our QDIT, or our register for logical qubits. So this is nice because it's the longest lifetime of the thing we have. Also, it's very nice because it has a very simple error model. As well as we can tell when we build one of these oscillators, it has only photon loss. The rates of photon gain or pure dephasing in the cavities are immeasurably smaller, at least 1.5 to 2 orders of magnitude smaller, which is what I can tell, okay? So that means your job, again, for error correcting is made a little bit easier. And now, of course, in this platform, we still have transmons. We need nonlinearity in order to do anything interesting, to do the measurements, to do operations, and all of that sort of stuff. What I'm sort of showing in a cartoon here is a common thing now in the lab. This is a transmon that has sort of 3 little antennas that couple to 2 of these high Q modes and also to another on-chip readout. So you can use this guy as an ancilla. And basically, it's RF pulses and things. Everybody's fixed-tuned here that are going to enable the nonlinear interactions or all the kind of interesting stuff in this system. Okay, now let's talk a little bit about how we encode the information, or the ways we can encode the information in one of these oscillators. So our logical qubit is a continuous variable system, right? So we're going to see a lot of pictures of Wigner functions in X and P space. And just to remind you, for example, a coherent state, alpha, is just a little Gaussian blob in that space. So there were some really prescient works by a couple of fairly smart people here. Many years ago, these so-called GKP codes are things like this. They're superpositions of squeezed states in both X and P. There are these cat codes that I'm going to tell you about a little bit more that basically are formed from superpositions of 2 different coherent states as the code words. And there's actually now a very active interest in a few different groups on coming up with other kinds of clever and useful versions of these codes. And something I want to emphasize is we now have the tools to build all these things. So don't hold yourself back. Be creative. If you can think of some crazy state involving up to 10 or 15 photons, we can build it, we can play with it, we can use it. And just sort of to put in an advertisement here for some of the theory members of the team. So there's a poster or 2 from some of Liang's guys, and it's also in collaboration with Barbara, about kind of comparing some of these different codes. And the point here is, so what we're showing is the entanglement fidelity as a function of the probability of a loss event. And there's sort of the usual cat code, which is just a first-order code. And then there are various things, these binomial or numerically optimized codes. There's the GKP on a square lattice or on a triangular lattice. And the point is, even with a smallish number of photons here, one can make codes which, in principle, could be quite resilient and give you higher order correction against this photon loss. Okay? So far, we haven't built those codes or played with those yet, but there's a chance for kind of just in software upgrading these kind bosonic encodings. Okay, so again, in most of the experiments I'm going to show you, we're working with the cat code. By the way, from now on, these are theory. From now on, every Wigner function you see is experimentally measured data. I always forget to say that. So that one's experimentally measured. Those are cartoons in PowerPoint. So the idea here in the cat code is we're going to use this two states as our 0 and 1 logical. So if you like, it's a superposition of an X pair of coherent states and a P pair of coherent states. So in general, one of our code words will look like this. It'll be this 4-component Schrodinger cat with this nice cross-hatching in the Wigner function. And if we make it out of these symmetric superpositions here, both of the code words have even parity or even photon number. And so the Wigner function is red there in the middle. And the idea of this basically is if we want to correct against photon loss, we can have any of these superpositions, and we monitor the parity. And if a photon is lost, we know that we were starting even. We go out to some odd state, and we can detect that it's now odd, and we know that the error has occurred, and therefore it doesn't hurt us anymore. We can compensate for it. So let me show you an experiment. This is from a year or so ago, where we actually ran this cat code as a full memory in real time and got to kind of the break-even point. So essentially, the idea is here. We have a cavity that we're going to use to encode. We have a transmon qubit, just talking about it as 2 levels here, and this dispersive interaction where basically the frequency of the transmon is shifted by, let's say, 1 megahertz for each quantum 0, 1, 2, 3 of energy we add into the storage resonator or the logical qubit. And that's really kind of a neat thing because it means that parity monitoring is kind of precompiled into the hardware in a way, right? So all I have to do is 2 pi/2 pulses on the transmon, separated by a few hundred nanoseconds, and then I map the state of the qubit up or down onto whether the state in the cavity is still even or it's changed to odd. We can do that measurement very rapidly and with pretty high fidelity. And moreover, it's highly QND. So we've measured that there's less than a 0.2% chance that you actually absorb a photon when you do this monitoring of the syndrome. And as you see here from this real-time trajectory that was obtained on just a 2-component cat, you can get very high fidelity for knowing the parity, and you can make hundreds of measurements of the error syndrome in between the sort of few hundred microsecond time scale that a typical error does occur. So this is really a crucial step if you want to build an actively error-corrected memory. But then there's a significant amount of complexity from going just from that measurement to actually being able to perform the error correction. So in this experiment that was published in Nature last year, we did the following thing. We took a bit of quantum information. I'm going to try and separate the qubit, which is the information, from the transmon, which is a carrier, from the cavity, which is the logical. Okay? So we take a bit of quantum information, one of any state on the Bloch sphere. We encode it into the cavity, and then we can do what I call the debugger view here. We can actually put a breakpoint in, measure the Wigner function, and say, yep, it encoded correctly. Then we can wait a little while. We interrogate the error syndrome. And there's a FPGA controller that in real time decides, I think, an error or not an error. And you can put a breakpoint in, and you can see that, yeah, when it thinks there's an error or not, it's incorrectly sorting the states. We can do multiple rounds of this. We did out to 10 or 20 rounds, but there's actually no limit in the hardware or the software for what we can do. And then basically, you get all these kinds of trajectories of whether or not there has been an error and how many errors there have been. And you can sort these, and you see that even when you have detected an error, there's still coherence on your Bloch sphere, because knowing that the error occurred, you know where you went on the sort of logical Bloch sphere. And so we can realign all those states and look at the process fidelity of this memory. We stored the qubit. We tried to retrieve it. It's the simplest circuit family. Where's Daniel? I saw him there. It's the very simplest circuit family. We're just doing identity. OK? And there's various ways we can try to do identity. We can put it in the transmon, or we can put it in this sort of very faint black here in the sort of best physical encoding in the system, 0 or 1 photons in our longest lived box. And when we do the cat, there's an overhead. We have to use several photons, so you give away a factor of 2 or 3 in the lifetime right away. But when we turn the error correction on and we use the information obtained by the controller, we actually see that the process fidelity goes up. It goes up by a little over a factor of 2 and just barely beats the performance of the best physical component. So we're sort of right at what we call the break-even point. I think it's sort of similar to whatever definition number 4 or 5 of fault tolerance was. OK. So you might be a little disappointed, though. We got the error correction to work. We're doing all this effort, and we only got a factor of 2. How come? Well, the best thing is this is working exactly as well as it's supposed to work. And I just want to remind you that there are lots of ways that even a correctly constructed error code can fail. The first thing is we were only using a first-order code, so we could have double errors. Now, again, I'm able to monitor at a rate 100 times or 1,000 times faster than they occur. That should be pretty small. There are potentially uncorrectable errors. I said those are very small in this system, but maybe they're not 0. We can have errors in the readout, errors in the preparation of the ancilla. We can have undesired couplings of other sorts. And most importantly, we can have forward propagation or non-fault tolerance in this system. So this measurement we were doing is not a fault-tolerant interrogation of the syndrome. And so we can look at all of these error processes and match them up with the physics of our device and put together a budget. It turns out that in order to get the best performance, we had to slow down the rate of error checking because the dominant thing in the budget here is that we're not fault tolerant against energy relaxation in the transmon ancilla. When that relaxes, if we're doing during a interrogation of the error syndrome, it induces a frequency shift or a giant phase, which is not correctable currently in this scheme. Okay? And so this is the same thing you would find if you have like the 7-qubit Steen code with 6 ancillas. You'll be limited by this process. You have to go to the 24 ancillas. Okay. All right, so we can do some error correction. But how do you actually manipulate these things and do the gates? Just check on our time here. OK, plenty of time. So we have to manipulate these states, which again are a many-photon kind of complicated superposition in this cavity oscillator. So here's one way that we've worked out how to do this using some tricks from optimal control. So here's a kind of a cartoon of one of these cavities and its transmon that's coupled to it. And again, we have independent microwave drives. We can put in signals that will actuate the transmon, and also we can do displacement pulses on the cavity. And so what we're doing here in this example is we're going to synthesize the following operation. We want to go from vacuum to 6 photons in the box, which is not something you can do with just displacements, and that's a kind of hard, many high-order nonlinear kind of thing to do. So what do? Well, we measure the Hamiltonian of this coupled system. We measure like 6 or 7 important parameters in the Hamiltonian to resolutions of a few hundred hertz out of a few gigahertz. You put that all into a box, including the calibration of your RF drives, and you tell it what you want to do and run grape, and it says, play that weird-looking waveform on the I and Q channel of the transmon and that weird-looking thing on the I and Q of the cavity. And if we then play parts of these pulses and stop and we look at the probability of the photon number distribution in the box, it goes all over through some complicated trajectory in this Hilbert space. And eventually it kind of converges here on n equals 6. And if we make the Wigner function, again, this is an experimentally determined Wigner function, you see this beautiful thing with 6 rings, which looks like a fairly high fidelity copy of n equals 6. Okay? So we can use this kind of technique now to do operations on one of these encoded 4-component Schrodinger cat states. So for example, here's data which are showing sort of a pi pulse, or actually 2 pi over 2 pulses, that are flipping the state of the logical qubit inside this encoded oscillator. So what this operation corresponds to go from here to here, you have to go from all even photons. You're going from 0 mod 4 in the box to 2 mod 4 without changing the actual photon number on average. And that thing is the square root of that operation, whatever that is, right? And so you can do this. You can put these all together. We can do, by the way, both Clifford and non-Clifford operations with this technique. And we've measured process tomography on all the gates. Again, efficiency, we can do that. Process tomography on single logical qubit operations. And just to show you something sort of easy to understand here, this is just randomized benchmarking on those Clifford gates, showing that basically we have 98 to 99% fidelity. You get the same answer from the process tomography. And again, we understand what this is limited by. This is dominated by the fact that you're entangling with the transmon. These gates take a few hundred nanoseconds, and that's the decoherence rate in the transmon. Okay. In fact, in this experiment, they didn't even bother correcting for photon loss, or even just the deterministic shrinking. That was completely negligible, even over hundreds of operations on the cat. Okay. A big separation of timescales here. Okay, so now let's talk about how we can actually think of entangling two of these cavities and doing operations, doing entangling operations between the actual cavities. So there's a couple of different ways to do it. Again, you need the nonlinear element. You need your transmon. We can do a fast operation where basically you sort of swap the information into a transmon and then into the other cavity or analogs of that. Or we can use the transmon in a sort of indirect way where you directly convert, let's say, states from one oscillator to the other using some four-wave mixing kind of thing. And so this one is faster, basically can be done in hundreds of nanoseconds. This one tends to be a little bit slower, but we're increasing the speed quite rapidly. And the advantage of this scheme is that you actually can do things in a way which is insensitive to the transmon decoherence. So first, let me show you an example of the direct one. So this is, again, a measured Wigner function. It's the joint Wigner function of two of these oscillators using this Y-shaped transmon. So you're measuring is the sum of the photons in Alice plus the photons in Bob even or odd. Okay? And what we've done here is a little protocol that should create the following state. It's a cat state that lives in two boxes, or if you like, it's an entangled pair of two-component cats. With about beta equals 2, this pair of logicals is living in a Hilbert space of dimension 150, 200, something like that. Okay? And you can do the tomography. And here's what you see if you take a cut in one of the other axes. So now the Wigner function is actually a four-dimensional thing, so I'm showing you a couple of two-dimensional sheets. You see both regions of negativity and fringes indicating that this thing is really coherent. And you can even do things which are a measurement. You sort of measure special cardinal points in the Wigner function, and they correspond to measuring in a single-shot way kind of the projection along X or Y or Z logical of each of the two cavities. And we can build up something which is like a Bell witness and show that we're violating a Bell inequality. And this is no correction for readout, by the way. So we know that we have now entangled these two cavities. Okay. But we want to do more. That experiment was sort of just a trick, if you like, a shortcut to making that particular state. What we really want to do is have generalized kinds of operations. This is showing you some preliminary work on being able to do operations between the cavities. Here what we're doing is a kind of virtual driving with RF to swap a single photon back and forth between the two cavities. And the thing I like about this is the time axis. So here the swaps are slow, but they're persisting for about a half a millisecond, which is much longer than the lifetime of the transmon. Okay? In fact, it turns out that you're insensitive here to both the relaxation and the dephasing of the transmon. The limiting thing here is there's a finite heating rate of the transmon. If it goes into the upper state, again, we get that back action dephasing, and that's what's causing the decay of these oscillations. I believe in this experiment, both cavities were of order 2 milliseconds long. And so this is a sort of step against, in the way I'm as an experimentalist going to use the term being fault tolerant against certain forms of error in your ancilla or in your transmon that's letting you do these gates. Okay. All right, so the final topic here I want to tell you about is this recent work, which we're just writing up on a teleported gate between two of these CNOTs. So again, to remind you, what we need to have here is kind of two modules. Each needs to have a communication qubit, which here is going to be a transmon, and a memory qubit, which is going to be, in this case, a pair of long-lived microwave cavities. And by the way, in this hardware, we're able to change, just in software, the encoding scheme we use in those cavities. And so I'll show you a couple of different versions of that. So this is going to be a teleported gate. It's not a remote teleported gate. Here the modules were sort of soldered together, if you like. There's a bus that directly connects the two transmon qubits, just so we can do that entanglement relatively well. And here's, again, sort of this scheme for the teleported gate, if you don't remember it from earlier on in the talk. So there's a bunch of resources here. You need 2 of these Wymon qubits. You need these long-lived cavities. You have a coupling bus, and you also have independent readouts on both of the transmons, 2 parametric amplifiers, and it's all run on one little FPGA system about like that with custom software. So here's kind of a more detailed thing of what the pulse sequence looks like. First, we prepare some states in these 2 memory cavities using, again, these optimal control pulses. Then there's a little scheme here, which is producing the bell pair between the 2 transmons using one of these RIP gates that Hani mentioned, basically RF driving of that bus resonator to create the entanglement. Then we do, again, the operations between each transmon and his memory cavity. Those are done with, again, optimal control. We measure, and we feed forward and do correcting operations. Okay. Sorry, I was supposed to be clicking as we went. And again, we can do process tomography on that gate between 2 logicals. So in this case, I'm showing you the simpler case where we use the Fox state encoding of 0 or 1 in the cavities as our logical representation in the memory qubits. And you see here that it looks like a C0 should. And by the way, this is sort of doing the correcting pulses and realigning. There's 4 outcomes depending on the 4 classical results you get from your measurement of your communication ancillas. And they all have pretty much similar fidelity, but we can coalesce them all together here. So the fidelity is not great. In that experiment, all of the little pieces work between 95 and 99% fidelity, but there's a bunch of them, right? So the overall fidelity is something in the range of 80%, where I'm being sort of conservative and saying I won't take out the state preparation at the beginning and the fidelity of the measurement at the end, and so on. We've not yet done randomized benchmarking on this, but that would be a nice thing to do next. But what's even nicer here is, like I said, we can extend this and now apply this to do a C0 between 2 logically encoded qubits. Again, we're not going to run the error correction yet, and it wouldn't help here yet, but it's possible. So the 2 code words we're going to use in each of our cavities are the following. They're sort of the minimal instantiation of the cat code, or it's a binomial code. The 0 logical is the 2 state, and the 1 logical is 0 plus 4. So they each have the same photon number. They're both even. So you correct for single photon losses. So I'll just show you the truth table. We can also do the process tomography in this case. So here are the input states. We have memory qubit 1, which is the control, and memory qubit 2, which is the target. And when we start, of course, with the control in 0 logical, which is the 2 photon number state, then what you get back here is the same thing. And of course, I wouldn't be showing it to you if it didn't work this way, right? If we start with the 1 logical in our control qubit, then you see that these guys switch sign. Okay. And again, you're doing, I mean, this is not just, by the way, tomography in the logically encoded space here, but when you do these Wigner functions, a neat thing is you can see if there's leakage, right? If we were getting something crazy here, there'd be signal outside of this. So it's a kind of a powerful thing. Okay, so how are we doing here in this sort of roadmap or this plan of baby steps towards error-corrected quantum computing or working with logicals? So we've done all these things, creating the code, measuring the error syndrome, tracking, getting to lifetime extension. Essentially, we're here. I'm showing you how we entangle 2 logicals. There's also work, which I don't have time to talk about, from Michel Deveray's group, in which they are stabilizing continuously a 2-component cat and they can do sort of Rabi oscillations on that cat. So it's like 1 qubit operations while continuously correcting. So there's a lot of work still to do, but I think, again, the point here is that with a little bit of cleverness and some of these shortcuts, you can really address many of these interesting questions in the lab already. So let me thank all of the many collaborators we have at Yale, all of the team members and everything, and just put up some very faded out versions of things, and I'd be happy to take any questions. Thanks.
Okay, any questions for Rob?